What if the universe isn't random at all, but instead governed by beautiful and precise patterns? Welcome back to Infinity Beyond. In this episode, we journey into the hidden architecture of the cosmos, an architecture sculpted by symmetry. Symmetry in physics goes far beyond aesthetic appeal. It's the invisible blueprint behind the most fundamental laws of nature. But what does symmetry really mean? At its core, symmetry is about invariance, the idea that certain properties remain unchanged under specific transformations. For instance, if the laws of physics work the same today as they did yesterday, we call that time translation symmetry. If those laws apply equally everywhere in the universe, that's spatial translation symmetry. And if the universe doesn't care what direction you're facing, that's rotational symmetry. These concepts may sound abstract, but they have concrete, observable consequences. Enter Noether's theorem, one of the most profound results in theoretical physics. Proposed by German mathematician Emmy Noether in 1915, the theorem states that every continuous symmetry of a physical system corresponds to a conservation law. Let that sink in. Time symmetry? Conservation of energy. Spatial symmetry? Conservation of momentum. Rotational symmetry? Conservation of angular momentum. In other words, the predictability of our universe stems directly from its symmetrical nature. Without these symmetries, reality would be chaotic. Motion would be unpredictable. Stars wouldn't form. Life might not even exist. But here's the deeper question. Why does the universe have these symmetries at all? Are they fundamental features of reality? Or are they emergent properties of deeper physical laws? Some physicists believe that symmetry is not a choice, but a requirement for the consistency of any physical theory. Others argue that what we perceive as symmetrical laws are simply the only ones compatible with the kind of universe we can observe. That life and complexity demand such order. Let's take a closer look. Imagine a universe where energy is not conserved. In such a place, perpetual motion machines might exist, or time itself might behave erratically. The result would be a chaotic and unintelligible cosmos. But because of time symmetry, energy is conserved, and the universe behaves in a stable, predictable way. The same goes for momentum and rotational symmetry. Think about our solar system. Planets orbit the sun in consistent patterns thanks to the conservation of angular momentum. Remove symmetry, and the celestial dance collapses. In particle physics, symmetries are even more profound. The standard model of particle physics is built entirely on symmetry principles, known as gauge symmetries. These internal symmetries explain how fundamental forces, like electromagnetism and the weak force, interact through force-carrying particles like photons and WZ bosons. Without symmetry, we wouldn't have quantum electrodynamics, QEDD, or the electroweak theory that unifies two of nature's forces. Symmetry even predicts new particles, as was the case with the Higgs boson, which completed the Standard Model's picture. But as our understanding deepens, we find that not all symmetries are preserved. In some cases, the universe undergoes what's called symmetry breaking. A perfect example? The early universe. Shortly after the Big Bang, it is believed the universe was in a highly symmetrical state, a kind of quantum soup with all forces unified. As it cooled, symmetries began to break, causing the separation of fundamental forces. This breaking is not random. It's a phase transition, like water freezing into ice. The underlying laws remain, but their expression changes. Symmetry breaking gives rise to complexity, and complexity gives rise to everything from atoms to galaxies. This also happens in materials, science, cosmology, and even biological systems. So now we come full circle. Symmetry offers both structure and freedom. It dictates the rules, while allowing for rich diversity through breaking and variation. It also raises the tantalizing possibility that the universe we observe is only one of many, each with different symmetry structures. Could our universe be just one pattern among many, selected by chance or necessity? In string theory and multiverse models, different regions of reality may exhibit different symmetry laws, some allowing life, others not. We may never know the full answer, but what we do know is that symmetry provides a lens of clarity, one that reveals hidden unity beneath the chaos. It links time and energy, space and momentum, motion and meaning. As we continue our exploration of the cosmos, symmetry may guide us to the ultimate truth, not just about physics, but about why anything exists at all. So the next time you see a snowflake, a galaxy, or a perfect circle, remember, you're glimpsing the deep design of the universe, written not in ink, but in symmetry.